Okay, so today's paper is going to be on contextual position encoding. So this came out of Meta Fair, and this paper is just a new type of position encoding. And so, in order to actually explain how it works, we're going to get started by, of course, reading the abstract. So I'm going to start with the abstract. The attention mechanism is a critical component of large language models, LLMs, that allows tokens in a sequence to interact with each other, but is order invariant, right? So if we go to the thing on attention is all you need, each attention block is actually order invariant, right? It doesn't actually particularly care about the order of the thing. So that's why we introduce a position embedding to the attention block, right? So I'm going to make a new diagram here, right? So each token that goes into an attention block is just directly combined with every other token, right? So let's say we have like a few tokens, right? I'll make it a little bit bigger. The attention block, right? So we're just going to feed it through attention. Attention. The attention block just has no knowledge of like the order of these tokens, right? So if I just like put these in, it has no knowledge of the order because it just applies the same operation on every single token, right? And so in order to actually like add position, each token itself needs the position embedded within it. And that's where position encodings come in, right? So before it goes actually into the attention layer, I'm just going to skip the other embeddings. We're just going to have it go through. I'm going to move this over a little bit more. We're going to have it go through a position embedding, right? And so this position embedding, now each token, let's assume you just have some words, right? Like the sky is, right? Some tokens, right? Now, after the position embedding, effectively what you have is the exact same tokens, right? Nothing has changed about the tokens, except for now, they contain a little bit more information on the actual contents, right? So this is the, and the position is 0. Then you have sky, and the position is 1. Then you have is, and the position is 2. And so now the attention layer actually knows the order of these things because it knows the position of where each like token is in the words, right? Otherwise it wouldn't know it that. But of course, now what Meta is saying is there's a new position encoding, right? Because I'll explain how it works previously when they get to it in the paper, right? And so as they say, incorporating position encoding makes it possible to address by position, such as attending to the ith token. And so the issue with the current methods is current position encoding methods use token counts to derive position and thus cannot generalize to higher levels of abstraction, right? And so if you have an LLM that you want to say understand sentences or whatnot, if you have say a long paragraph, but then you have some longer sentences that don't really say much, and then some shorter sentences that are very important, right? Like your thesis sentence is going to be very important to that paragraph, but then some other sentences with a lot more tokens probably aren't as important. The LLM doesn't actually know the like structure of the paragraph. It has to actually learn that through its training. Whereas if in the position embeddings you're able to encode this structure, right, like the structure of your paragraph or whatnot, what you're able to do then is the LLM is basically just able to learn the basically the LLM is just able to learn that from the start, right? Like it starts with that as baseline knowledge. So it knows, here is a sentence. Now I can go off of this to then later, do better, right? And so in this paper, they have a new position encoding method, contextual position embedding, or copy, right? So contextual, position, encoding, e. Copy. I'm not going to call it cope because, yeah. And that allows positions to be conditioned on context by encoding positions only on certain tokens determined by the model, right? And so you now have more general position embedding. So in essence, what they're saying is they have figured out a way to embed this type of information into the position encodings, right? The position embedding, the position encodings are now effectively containing all of this information. And so let's figure out how they do this, right? And so they basically say the transformer architecture, they say, relies on the attention mechanism, right? And so it is necessary to have an additional mechanism for encoding position information, right? Because the transformer architecture is unique in that with recurrent neural networks and convolutional neural networks, the positioning information was just kind of just part of how the model worked. Whereas here, you have to add that information back in. And so position itself can be measured in two ways. Absolute position embedding count, that's at the start of a sequence, right? So if we go back here, right, this is what we have here, like the 0, 1, 2, right? So we just start at the start of the context window, you just go 0, 1, 2, 3. And the LLM can learn from there. And you have relative positioning that's like backwards, right? So if instead of 0, 1, 2, it goes 2, 1, 0, right? Like 0's token is the most recent one, right? And so obviously position embedding is important. And current position embedding methods use tokens, right? So tokens, they're the unit of measurement. You use tokens to actually do neural networks, so that's just a pretty easy way to do things. Like, it's an obvious way to do things. However, a token is a variable unit that can be part of a whole word, part of it, or even a character, right? So, for example, if you have, say, the text, I'll just copy these over. If you have the text, the sky is, and then you have the tokens, for example, a multi-token word like uninhabitable, so you have un, and then inhabit, and then able, right? Like, the LM could say the able part of this thing is of equal weighting to, say, sky, right? Which in this sentence, they're really not, right? Like, this is the subject, this is the object, and we haven't fed that specific information into the LM. The LM is not able to know, right? And so, in order to tie position measurement to more semantically meaningful units as words, which is what we actually want, right? Like, we want it to be like, uninhabitable, that's a word. That should be one, like, embedding point, like, one space in the sentence. Sky is one word. It should be one place in the position embeddings. They need to take context into account. Again, contextual position embedding. Copy. However, this is impossible with current position embedding methods, because obviously you don't know where the context is, right? And so, again, they have a new method. And here's a new method, contextual position embedding, right? So here they're splitting it up by sentences, right? So here they have some text from Alice in Wonderland, and so here's the old one, right? So you have effectively gradual decay of what you're looking at. You have a period, a rabbit came, right? So you have 12 tokens, but the LLM, it's like, oh, you probably want rabbit to be one token. Or maybe you even want the entire sentence to be one token, right? And then the LLM can, like, figure it out, right? And so, in essence, now you're computing values with context first, and you're using that to assign positions, right? And so now, if you have the attention block, right? Now, the attention for, say, the current token will gradually decay over time, right? Because this is just how LLMs work. They start at the present, and then they'll, over time, they'll, like, gradually decay the further away you go, right? But now what you're able to do, you're able to just have the attention, say, apply a lot more to the current set of position embeddings, and then so the decay is now more, it's arguably better, because now you're dealing with entire sentences and whatnot, right? And so they call it contextual position embedding, copy, right? So given the current token as a query vector, they basically, so copy first determines which tokens to count using the context vectors, right? So basically now what they're doing is effectively they explain it later. But yeah, so I'll explain it when they actually explain it. So they apply copy to toy tasks, right? So they haven't actually scaled this up crazily yet, but they've used it on a bunch of toy tasks, right? So counting, copying, and the flip-flop tasks, and they'll explain those a little bit later, where it outperforms token-based methods. So to test real-world applicability, they use the Wikipedia test, where they show at least a better performance, right? So this quick test on real-world application. And the same performance gain is also observed when training on code, right? So they have some background on position embedded encoding, which we can just kind of skip, because, again, it is just, you have it, like, go have a different number for every one. And this is actually really similar to the vision transformer paper, right, where we just have a number that goes to like 0 to 16, right? And so, again, their motivation is that standard position encoding fails on simple toy tasks, right? And so, to actually show the toy tasks, yep, here we go, right? So, in essence, you have the test from Alice in Wonderland, where it's very tired, yeah. So you notice the word Alice shows up 3 times, and the word book shows up twice. And so in GPT-4, they say the word Alice is mentioned once, which is wrong. Llama 270B also gets it wrong. It's mentioned twice. No, it's mentioned 3 times. That's wrong. And then if they fed it again, but ask for the word book, GPT-4, it's mentioned once. That's wrong. Again, this is just like the models are wrong. Llama 270B just kind of happened to get it right here, right? So now we're talking about contextual position embedding, right? So in contextual position embedding, positions are measured in a context-dependent way, right? So we know this, right? And so a gate value is computed for every query and key pair, right? So you have a gate value, and it just passes through sigmoid of the query and key. So in essence, what they do is, in order to do position embeddings, they just effectively have a small mini attention layer, right? So they have a small mini attention layer, and so that mini attention layer is going to be like, hey, which one of these is a gate? So if we go back up to the diagram, the gates, it's learned that the periods are the gates here, but now you can have an LLM be like, hey, actually I want, say, reading to be a gate here, right? Because it's a very important thing. I want to split this sentence up into 2 sentences or whatever, right? And so, in essence, what they're doing here is they're effectively just running attention on the tokens themselves to find out what the position embedding should be, right? It's going to find all the important stuff, right? And so, and note if the gate's always 1, then, right, and so, in essence, the position values are just, they add the gate values up until that point, right? So if you go back up here, they just start at the start, and then they just say, oh, gate's 1, let's just add it up here, gate's 1, right? Like, pretty simple stuff, right? And so, unlike the token positions, their positions are not restricted to integers and take fractional values due to sigmoid, right? And so now, if we go back up here, this doesn't have to be, say, always 1, right? This can be like 0.5, right? Let's say, like if you're in like the middle of a sentence, right? If you have like a compound sentence like, Alice was tired, so she decided to go to bed, right? Now, the LLM can be like, oh, the comma in that sentence is actually like a half thing, right? So now what you have is the first half of the sentence would get, say, 2.5, and the second half would just get regular 2. And so because these are floats, yeah. So you can have any range of values, and it's trained, right? So you would just run an attention layer to calculate this, right? And so then you can interpolate it, and yeah. And so you have limited positions. They define it for single head, but you can do it on multi-head, right? You're just running an attention layer and then combining it together. And so computation is the most computational operation in the attention is the key query multiplication. This is effectively, you're running into the same problems that transformers get you, right? So you have the problems with transformers, and so now effectively what you have to do is you bring that into the embedding space. So instead of just having a number go up, you have effectively brought those problems into the embedding space, right? So it goes up with the square of the context window, right? And then obviously you have to actually do actual computation here because you can't just do nothing. So we ran some experiments, right? So you have the flip-flop task, right? And so basically the flip-flop task is you have to capture reasoning over long range inputs, right? So there's a lot of inputs. And so it's an alternating sequence of instructions, so write, ignore, read, and it's a bunch, and it's followed by a number. So you write 0, you ignore the 1, you read the 0, you write the 1, right? So the expected output is 1 because you're writing the 1 and you're just ignoring a bunch of stuff, and then you're reading at the end, right? And so the last few operations, right? So this is just a task. It's just you have a very simple task. You're effectively turning the LLM into a Turing machine for the flip-flop task, right? And so they report test error after 10,000 training steps for models they just have a bunch of models, and here's a table, right? So contextual position embedding, they effectively just like solve it immediately, right? And in relative embedding, which is where they have they require all 10,000 training tokens, whereas contextual, it's like, as you can see, it just does so much better on this task, right? You can effectively build a, what's it called? You can effectively build a Turing machine now very simply, right? Obviously, increased number of variables cause more errors, but, you know. Then you have the selective copy task, which is effectively, you have an input sequence where you just remove a bunch of characters, right? So you remove all the B's. And so, again, it performs better. Counting task, again, much fewer errors, it performs better. And the wiki text, as you can see, the perplexity, which is a measure of just how good a model is, again, it's a lot better here, right? Like they just have, and so obviously they have relative. So relative, so I should probably explain. Absolute is just going 0 to like 0, incrementing starting to end, whereas relative is ending to start, right? And so, as you can see, you want relative, it's useful, right? And so they're basically testing how well it generalizes, and as you can see, the contextual position embeddings, obviously you have the curve where as the context window goes up, you get more errors, and so, but the contextual position embedding just does a lot better, right? And so here is the actual key query, right? As you can see with so if you have contextual position embeddings focusing on current paragraphs, you get something like this, but if you have it on sections, you have it on this. And so you can effectively have like multi-headed type stuff going on here, right? And you can separate it by section titles and whatnot. And so they have some related work here, but yeah. So now that's what a contextual position embedding is, right? It's a way to do position embedding for language models in such a way that you're able to, split it up based on the actual text itself and not anything like arbitrary, right? So if we go to the draw.io, if we take this text, the sky is uninhabitable, right? So I'll just have this be a regular text, right? So let's assume this is just regular, like rope. So this is just the regular, just number go up, right? That's the thing. Text size, make it a little bigger, right? So you have rope here, right? So this would be 0, 1, 2, 3, right? So it just increments, right? So you just have it effectively increment up through the thing, right? Then, if you have, say, contextual position embeddings, right? But this isn't relative, this is just absolute, right? So you're going to have, say, 0 here, 0 for sky, 0 for that, and then let's say uninhabitable gets its own thing, right? Because that's a pretty big word, you probably care about it a lot more, right? So now you have effectively contextual embeddings, right? It's embedded based on context. And because this is part of a sentence, let's say this is 0.5, right? Right, so now you have like words and like part of a sentence and whatnot. And then obviously, if you have, say, absolute, you would flip this. Where is flip? Okay, I don't know how to flip this. Cool. But like, relative would just be flipping this the other way, right? So you'd start from the most recent one and you'd go all the way back to the end, right? So, in essence, that's the main difference between contextual position embeddings and the old method. And now, of course, this paper is very new, right? Like, if we go to the arXiv, this was released on the 30th of May, right? So this is like 3-4 weeks old, right? So no major models have come out with this, but you can probably imagine that later models will come out better with this, right, over time. So now, so effectively, in summary, contextual position embeddings are a new way to embed text within, like feeding it into an LLM, more specifically a transformer-based LLM, that makes it more efficient for the transformer to learn different parts of text, right? Because when humans are thinking about text, they think in sections, they think in sentences, they don't think in individual like parts of words, right? Like tokens. And so this is just a new way to do that. And so as they say, it's learning to count what's important. And I think I'm going to leave the stream there. We've covered the contextual position embedding paper by Meta. And again, as always, the mind maps are available. They're on my YouTube, which I should really link to on my Twitch. I'll do that after the stream. And yeah, that's basically everything. I will see you guys all in the next stream.